Hello and welcome to this video. In this video we are going to look at some uses of radioactivity. So far we've come up with this kind of theory of radioactivity. We know what is happening. We have a general idea of how we can predict how radioactivity is going to happen. We can quantify things such as activity and half-life, and now we're going to see how can we bring all of this together to put some use towards it. Now the way I'm going to do this is I'm going to give you one example from each type of radioactivity, and then I'm going to give you a generic example at the end. So let's start with alpha decay. And the way alpha decay is actually used is in fire alarms. So fire alarms use an alpha emitter. And the way this works, so this is an alpha emitter source, is usually americium. And the way this works is that you have a source of americium, or something that's going to fire alpha particles at this across some gap, and this gap has a detector here, and this detector should detect these alpha particles. Now in between where the radioactive source is, this is where you'll have this ventilation, so air can come in and out of this area. Now what happens is, through air, the distance between the americium and the detector is small enough that the alpha particle will be able to be detected by the detector. As soon as we get smoke in here, we now have increased the density of the air, and so it will collide with the alpha particles. So the smoke collides with the alpha particles, and when it collides with the alpha particles, it stops them from reaching the detector, and as soon as the detector no longer detects the alpha particles, it will then sound the alarm. So it stops them reaching the detector, and then the detector will have some kind of switch that as soon as it doesn't detect anything anymore, the alarm will be triggered. And this is a use of alpha emitters. Now alpha emitters, apart from this, are not commonly used for much more. This is mostly because of their ratio of benefits to risks. The risks with alpha are pretty high for any kind of medical use, and also then we have the kind of ability of alpha to move around or be transmitted across large distances just isn't there. So fire alarms is probably going to be the only kind of use of alpha radiation that you hear about, other than things like the Rutherford scattering experiment and such. Then we can move on from this. We can say another use, for example, of a beta emitter is something called thickness monitoring. Now in thickness monitoring, the whole idea is maybe in a factory, they're producing either sheets of paper, sometimes sheets of metal, and they want to have the thickness of these sheets of paper or sheets of metal to always be the same. They don't want to produce paper that's too thick or too small, so they need some sort of feedback control system in order to make sure that we have a constant thickness. So the way this works, we have a beta emitter being used in this, and we're going to say that we have some rollers here. Now these rollers are what are going to push down onto the paper or the metal. I'm going to say for this example I'm just going to go with paper, and so this paper is going to run through these pressure rollers. Now these pressure rollers have a mechanism where they can push down or loosen off the pressure of this depending on feedback from a radioactive source. Therefore what is going to happen is we need some sort of beta emitter on one side of this sheet, and we need a detector on the other side of the sheet. Now what this is going to then do is the beta particles, if the sheet is thin enough, should be able to pass through. Okay, so they should be able to pass through, and the detector will read a somewhat consistent count rate. obviously the count rate will be proportional to the activity, so over time you're going to have to replace this beta emitter because the activity will become too low. But for the most part, you will end up with a consistent reading on the detector. Then what happens is if the rollers loosen off a little bit, then the paper will become too thick, or the metal will become too thick. If the metal or paper, let me stick with paper, if the paper is too thick, the reading on the detector is going to decrease. So the amount of radiation that it actually detects is going to decrease, because if the thicker this paper gets, the more chance it has of stopping this beta particle, or at least slowing down this beta particle significantly. If it was metal, you can get to a certain thickness where you can completely stop this. So if the paper gets too thick, the reading on the detector decreases, and this detector is then electrically connected to the pressure on the rollers, and then if the reading on there decreases, the pressure increases. And this then leads to, if the pressure increases, this pushes back down on the paper. Paper then gets thinner as it comes through here. Then what happens if it gets too thin? If we push too much, the paper is too thin, then the reading on the detector will increase. And if the reading on the detector increases, that is because we have now less material in between the radioactive source and the detector, and hence we're going to allow more of these beta particles to actually travel through. When that happens, the detector reading becomes too low, or too high even, and then when that is too high, we want to decrease some pressure, so the pressure decreases. And this will have to be a continuous loop in order to reach an equilibrium. So if we then decrease the pressure and then we put off too much pressure, then the paper is going to become too thick. Our pressure has to then increase. If our pressure then increases too much and becomes too thin, our pressure has to decrease. It's going to be a continuous cycle. But this is again another use of radioactive beta emitter. And a fair question to ask at this point would be, why exactly is this good for beta? For the alpha decay in the fire alarm, it's fairly straightforward that you want something that can be stopped easily, so that you will always have the ability to stop it just by adding a few smoke particles. In this case, we want something that can be emitted through, but will still change intensity depending on the thickness of something. If this was alpha, for example, and we had paper in front of it, alpha is going to be stopped by paper every time. So we can't see any variation in the thickness, because even if we have a very thin sheet of paper, we're still not going to be able to detect anything on the other side. Likewise, if we had gamma radiation, gamma will always pass through this sheet of paper. So again, we're not going to see any variation because paper is just not thick enough to be able to absorb any of that radiation and decrease this reading on the detector. So for this specific case, beta is the perfect source to use, because it's not so low energy that it can be stopped by things like paper, but it's not so high energy that it can easily pass through paper. There will be some sort of very slight variation in the thickness of paper, and leading to a variation in the amount of radiation that's detected. Now, a use of gamma radiation would be cancer treatment. Now, this isn't the only kind of use of gamma radiation, but this is probably the biggest one. And this is because gamma rays are the most penetrating, meaning that they have, because they're the smallest of them, because they have such a small wavelength, not only can they travel through your skin to get to the cancer cells inside your body, but they're small enough to go into an individual cancer cell. They're small enough to go into the DNA of that cancer cell and then cause an electron to maybe be knocked off somewhere, causing a mutation in that whole molecule, which is mutating then the DNA, and by mutating the DNA, you can potentially kill that cell. Okay, so the gamma emitter, and we use gamma emitters because the gamma rays can penetrate cancer cells and mutate them so that they die. So the whole point of that is we want to kill off the cancer cells. There is kind of a safety zone with this though, because a possible danger of this kind of cancer treatment is that we can't force the gamma rays to only kill the cancer cells. If they come into contact with a regular healthy cell, by all means it could kill that one as well. The gamma rays themselves aren't aware of the difference. They're not sentient. They will just go wherever they're fired and do whatever they do. So a potential danger is they could also kill healthy cells. Now, in order to kind of identify if this is a risk we're willing to take, we have to then think of what are the benefits of this treatment, what are the drawbacks of this treatment. Well, the benefit of this treatment is that it is effective, right? The benefit is that we can kill cancer with this method. We do have to know the position of this cancer, and we have to decide on a gamma emitter that has a relatively safe amount of radiation. This is where we're going to have to start comparing between different radioactive sources and their half-lives and activities. We ideally want something with a high enough activity so that it produces enough gamma rays that it will kill a significant amount of cancer cells. But we don't want to produce too many gamma rays so that it will then begin to just spread into more healthy cells. Obviously, the more gamma rays we fire at a person's body, the higher the chances that they're going to attack a healthy cell. So we need to identify the right activity for this radioactive source. Too high is dangerous, and too low is no longer useful. And so this is why we have to come up with these ideas. Now, another thing that I'm not going to go through in this video because I don't feel like it comes up in exam questions too much, but is another use of radioactive, like radioactivity in medicine, is something called a PET scan. So I'll write this at the side here. So it's positron emission tomography, and a PET scan is another type of process that uses radiation in order to locate where the cancer cells are. So this idea of cancer cells or even radioactivity being used in medicine is a very common thing. Things like X-rays are used in medicine all the time. And things like PET scans. PET scans are where you have an actual positron being emitted inside the body that then annihilates with an electron in the body and produces gamma rays that we can detect, and that allows us to pinpoint the tumours. That is then coupled with this cancer treatment. Now, this is why we have to be careful of what exactly are we exposing ourselves to or exposing the patients to, because too much radiation is obviously going to be dangerous. Too little radiation, we have no use for that. It's just going to be like a breeze. It's not going to help your body in any way. So as always with these, we have to try and find the perfect source, This is why we have to quantify this activity and half-life. And we'll talk more about the other dangers of each of the types of radiation in another video after this one. Now, the final use that I'm going to go through is carbon dating. So carbon dating is our final method of radioactivity. And for those of you who aren't familiar with the idea of carbon dating, this is basically a technique that we use in science, in geology, and archaeology and things like this to try and date very old organic material. So it's usually things like fossils. If an archaeologist in a field somewhere digs up a fossil and they think it might be a dinosaur tooth, then we need to figure out if that's true. If this is from a dinosaur, if it's from some other creature. So what we do is we apply carbon dating to this object, and we will see how old is this object, what kind of period in history is it going to fit into, could it possibly be belonging to a dinosaur, and so on. So the way we're going to do that is in all organic material, there is a very, very small proportion of carbon-14. Now, carbon-14 is a radioactive isotope of carbon, so this will emit radiation. Now, this is then analyzed. What we do is we measure the activity of the carbon-14. So what we do is we measure the activity. And now what we've said before is that we know the activity is lambda times n, which means that the activity is going to change over time. This then tells us that if we can see this idea that the activity is proportional to the number of particles in that system, we can come up with some sort of formula here where we can substitute that A is equal to A naught e to the minus lambda t, okay? Where A naught is going to be the initial activity that this carbon-14 had at the start of its lifetime, and A is now the activity that we measure. Alternatively, we can use this idea of measuring the activity to calculate how many radioactive nuclei are in this source, and we can then use that to, along with the n equals n naught e to the minus lambda t equation, we can calculate the time for that as well. And so then by calculating the time for these, we then can calculate how long this object has existed for. In exam questions, you won't be asked to use these two formulas to do this, although this would probably be a more accurate and maybe more scientific way of doing it. This can get very difficult, especially for some physics students who aren't also studying maths as well. So what we would say instead is they would tell you the half-life of this substance, and then they would say that this is the number of nuclei that we have in this system at this point. And we can even actually say that if we have this relationship between activity and the number of nuclei, where they're proportional to each other, if we say that the half-life, as we defined it, is the time taken for half of the undecayed nuclei to decay. Okay. We can also now say that if the number of nuclei is halving, and we know that the number of nuclei is proportional to the activity, that must also mean that the activity is halving. So our half-life can also describes the activity halving. Now what that means is if we then have the activity at this point in time, and we know what the initial activity is, we can then calculate how many half-lives does it take in order to get back to that initial activity. As soon as we do that, we can then see, okay, maybe this thing has gone through 7 half-lives. If it's gone through 7 half-lives, we need to then work out what 1 half-life of this thing is. If we know that, we can then say, calculate what 7 times that half-life is. Now, a common type of exam question that you'll get for this is maybe saying that, let's take the assumption that we have some sample, and the activity of the sample at the time that it first would have begun its life, it starts at 50 becquerels. Okay, these are random numbers. The numbers that you have will probably be not as nice as these numbers, but I'm just getting the principle across. So let's say the initial activity was 50 becquerels, and then when you measure the activity, it was measured to equal 6.25 becquerels. Okay, and now what we are going to say is if 1 half-life, so the half-life for this specific isotope was maybe 2 years, and we want to know how many years was this thing going for. We're saying that this is 50. If we divide it by 2 once, we get 25 becquerels. If we divide it by 2 twice, we get 12.5 becquerels. If we divide that by 2 again, so we divide by 2 3 times, that's when we get 6.25 becquerels. Okay, what this means is we've halved this 3 times. Therefore, this has lived for 3 half-lives. And if it's lived for 3 half-lives, we know 1 half-life is 2 years. Therefore, this has survived for 6 years old. Okay, obviously, when you calculate these, these will be much harsher numbers, I expect, but the method is the same. You want to see how many times could you divide that initial number to get to the new number that you have, and then you can calculate how many half-lives, multiply that by a single half-life. So these are then some examples for radioactive decay and its uses. So we have the fire alarms using americium alpha emitters. We have the thickness monitoring using beta emitters. We have cancer treatment using gamma emitters. And now we have carbon dating, which is just a generic idea that could use any of these types of radioactivity. Thank you for watching.